Okay, and so how do we create the rate function? So this rate function is essentially, how is it created? What does it consist of? The rate function, R, the approximate rate function. So I want to write the rule for the approximate rate function. Yeah, Autumn. Okay, and so how do I get those constant rates? What are those the values of those constant rates? So I'm using intervals of 0.9. Okay. Right, exactly. So the second interval, how would I write the rate for the second interval, Brandon? I want to write the rate for the second interval. How would I do that?
For the second one?
Uh-huh.
So it would be R sub h of whatever the starting one is. You said 0.9 would be 1.8.
So for the second interval, right? So this interval right here.
Oh.
R sub h of?
So the R sub h of 0.9.
R sub h of 0.9, or v of 0.9, right? And so then we can do that for all of them, right? So this was like the old way. We've started a new way, right? So I just want to review the old way. Okay, and so then what about the old way? So now we want to write this blue function over here is the approximate accumulation function built on these constant rates. And so just let's take a minute and see if you can write down what that function is. So can you write down what that function is? How are we doing? Can you just write it down? This is something we've done several times in many different contexts. Or just maybe just the first couple lines of it. You do the first 3 lines. Give you a chance to think about it. Should be starting to feel familiar now. Without looking at previous notes, close your notes. This is like, can you do it? This is not, can you look at your notes and to help you? So at this point, without your notes, see if you can write down what the A function would be. So there's no t's in it? So this is a function of t, right? So this is, t is increasing through intervals, and we're writing the amount of accumulation at any value of t. Karen, how'd it go? The second line, what'd you get?
Second one, I put A of 0.9 plus R of t, and then in parentheses, the t change was t minus 0.9.
A of 0.9 plus
R of t.
RT.
And then in parentheses, t minus 0.9. In the interval 0.9 to t to 1.8.
Same as this one. Okay, what do you think? Agree? Some people are nodding their heads. Brandon doesn't agree. Tell me. You're looking at the rate. You're questioning the rate R of t.
Yeah.
So.
I don't think so.
So what rate do you want?
I was gonna say just R. Well, that's right.
So if we're in this interval, what is R of t?
0.9. That's why.
Yeah, R sub h of 0.9. So it works, right? So that's the nice thing about doing this function. We'll get the right rates in the intervals that we want. So we can just rewrite RT every time.
The first line is what? Is it just R of t times t minus 0?
Yep, because there's zero accumulation before, right? So RT times t minus 0, then that's what Karen said, and then each one falls in, right? So we're going to do all the accumulation from previous intervals. It's going to be A of the right side of the previous interval plus the current rate times how dx, right? How far, or dt, how far we've gone into that interval. T minus 1.8, or t minus the left side of the interval. Okay, and so then what did we say? We said okay, so what is a of 5? That's what I'm showing here. What is a of 5? What does a of 5 mean? So if we said a of 5, what would that represent? Eunice. The height at 5 seconds. Who wants the height at 5 seconds? What do you think? Agree? That's the accumulation of all changes in height, right? Is it the actual height at 5 seconds?
No, it's all the heights.
All the heights before, but also including at 5 seconds.
It's the approximation.
What's that?
It's the approximation of the height.
Right. So it's all those things you were saying. It's the accumulation of changes in height. It is the height, but it's not the exact height. It's an approximation. Why is it an approximation?
Because we've been approximating the rates of change.
Right. It's this blue function is based on the black step function, not the actual red rate function. Right. So this a of t is created strictly from the black constant rate function, and so it's the accumulation of little bits of height to get the height at 5 seconds, but it's an approximate height based on the r function, not the r sub h function.
So it's the accumulation of all the previous heights to get an approximate height at 5.
Yeah, changes in height. It's an accumulation of changes in height.
Okay.
Yeah, so if you do the accumulation of heights, then you'll get infinity, because it's like taking all the h values and adding all the h values up. So you want the accumulation of changes, little changes in height, gives you the current height. But if you did accumulation of heights, you'd really get infinity, because there's an infinite number of heights in there. Okay. All right. So then we said we want to. So this is good. It's using really important principles. Y final equals y initial plus the change we get from m dx. Really important principles, but what was our goal? Our goal is to write this in one line, rather than a line for every segment or a line for every constant rate. We just want one formula that's going to represent that same function a of t. And that's no small task, okay? That's a complicated thing. So we started that last time. And what was the general idea? So the general idea was, let's look at a different way to approximate the height, and just let's forget about that function we built and just say, how would we get the height at a of 5? Do you remember what we said? How would we get the height at a of 5? Jesus? Do you remember there's just the general idea of how we would do that? Yeah, we want to still use the approximate rate function, but just get an estimate, or using the approximate rate function, get a of 5, but not like plugging into that function we just built, but what would we do to get a of 5? Remember? Kelly, do you remember?
Didn't we use the interval from previous to subtract it, like from 4.5 and subtract?
We didn't do any subtracting. Yeah, Brett.
We would add the completed intervals to get the accumulation, and then we would take the current interval and find the difference from this current.
Okay, yeah, that's the idea. But we're not adding intervals. What are we adding? Yeah, that's the right idea. We got completed intervals and we have the current interval. And so then to get a 5, we're going to add up what? Right. Add up everything that's been accumulated in the completed intervals, plus there's a little bit more accumulation in the current interval, right? You guys have a question? You good? So it kind of does it in a different way. And Yeah, it does. Yes, it does add that up. It adds it up, but it's kind of like not directly, right? So we're doing it like every interval has its own rule, right? So how would this thing get a of 5? How would you get a of 5 using this? What would you do? I want to use this to get a of 5. Which one? This one? This one?
Yes.
We'd plug 5 into here.
Yes. And that would give us
What's that?
and then that would give us so we plug it into there.
Right?
And then it backtracked
Right.
for us if we would be doing it.
It would take 4.5 and put it into here. And then in order to get that, it would take 3.6 and put it into here. So do you see it's just a different kind of order. It's getting the same value. But this way, we plug 5 in for t. It calculates the accumulation in the current interval plus all the accumulation from before. How do we get that? Well, we plug 4.5 into here. And that gives us the accumulation from that previous interval plus all the accumulation from before. You see, does it make sense? So it's kind of like a end to beginning approach, right? So it starts with 5 there and kind of works backwards. The function kind of works backwards to do it. When we want to just kind of see it from time 0 forward, right? So we did this last time. We got all the accumulation from the current intervals, which we just do. MDX plus MDX plus MDX plus MDX. So it has a much different feel than plugging into the function, right? But yes, you get the same thing. And then the current interval is another MDX, right? Rate times the little change in the current interval. And we add all those up, and we're going to get a of 5, the accumulated changes in height at 5 seconds. Okay, and so then we said, let's make sure we got our terminology straight, so let's practice this again. Okay, so take 2 minutes and figure out where all the single question marks represent values. Double question marks are like phrases, or they're not values, but they're ideas or phrases. Okay? Go, talk through it. Okay, so you guys are done. Sounds like. How about Sienna? What's the black single question mark then?
The black single line
Yep.
is the
Completed plus current intervals, the black. What do you think? Agree with that, Jessica? What do you think? The current x. Current x. That's just showing the current value of x. Okay. What about, what did we say this was? Andrea.
That would be, I can't even tell what color that is. That is your initial value.
Initial value. Initial value of x, where we're going to start accumulating, and we said we're going to call that a, right? We're going to call that x equals a. Okay, and then what about what's next? How about blue? The blue question mark. What is that, Rachel? dx. dx is variable or parameter? It varies in the current interval, right? It varies through the current, as x varies, it varies through the current interval. What's the single purple? Britt?
Is it the top one or the bottom one?
The single right here.
Okay, it's dx as a parameter.
Okay, but we don't want to call it dx, so we have another name for it, right? So dx is the variable, and what is the parameter? Delta x is the width. The width of our intervals, okay? And then next. I can never remember. So what is? I think it's this one. I don't know. All right. Double purple question mark. Kylie. Complete intervals. Double gold. Noel. current interval, and then the red question mark we actually haven't talked about, but we're going to get to that today. But in general, the idea of the red question mark is? Yeah, beginning x value, good. Beginning x value of the current interval, or the left side of the current interval. So now I can turn those all on because I know those are the next three. So completed, current, and it's actually a function called left of x, which we'll talk about today. And then, what is the red function? That's the exact rate. And the black? Approximate rate. Okay, cool. So we are going to try to get the one line A function. So let's try this. So here's, I'm pausing, I'm freezing that, but remember we got to think of x varying through intervals. As that happens, dx varies through intervals. So how much do we have at x equals 6.75 based on the approximate rate function, right? Based on the constant rates. What's going to be the general structure to come up with that? How much we have at 6.75? Kylie, what's going to be our general approach to come up with how much we have at x at 6.75? Good. Right. So now the only thing is now we just have a generic rate function. We don't know if it's for height or not. But yeah, but adding up all the accumulated changes from the complete intervals plus the current interval. So that's good. We have three complete intervals, and then we have the current interval. So the change from the completed intervals, m dx plus m times change in x, and then the change from the current interval. Okay, so I think this is where your questions pick up. And a few of you will share. I didn't make enough for everyone because I made the type real big. So don't look at your notes from last time. This is what we were kind of doing at the end of class last time. So without looking, we'll kind of start over here and kind of work through those questions and discuss, right? Discuss and answer those questions to each other. Okay, so sorry, that parenthesis on number 2, that should be with number 3. The parenthesis, the parenthetical on number 2, that's a comment for actually number 3, not number 2. Okay? Okay, so I wrote in the individual x values if we had 3 complete intervals. So are we in agreement about that? I think most of us got that. So then what's the x value that corresponds to getting the rate for the jth completed interval? So for any one of those completed intervals, how do you get that x value that gives you the rate? A plus. It's always a plus some number of delta x's, right? How many delta x's for the jth interval? 1 minus j? J minus 1. So there's number 2. Okay, and then what's the x value for the rate of the current interval? So what's the x value for the rate in the current interval? Anyone get this? It's the same thing. We're going to be taking a plus a number of delta x intervals. So the question is, how many delta x intervals? Well, so what will it be? She wants a plus our capital C delta x. Agree? Yeah, Leo. Okay, so what's being asked for? Is it the current? Are we asking for the current value of x? Yeah, so that would be, if we added dx, what would we get? If we added dx to this, what would we get? We would get the current value of x, right? We would go a out to our starting point, then we go across all the completed intervals, and then delta x takes us to x. But, right?
So we're just going to like the start of that interval.
Yeah, so the rate, where do we get the rate for the current interval? Just like we got the rate for the completed intervals. The left side of the current interval. So we want to, once we traverse across the completed intervals, we want to stop, because that's the left side of the current interval. Does that make sense? If we add dx, then we're just going out to x. That's all we're doing, is we're just going to x. That's not, if I go back. See, look, at x, what's the rate at x? Here's x. What's the rate? The rate's here. It's a little bit lower in this picture. But the rate we want is this one up here, which is from the left side. Okay, so if we add that dx, we're just adding up and getting x, but we want this x value to give us that rate. Better? Okay, so imagine that the current value of x is in the 101st interval, much smaller delta x's now. How could we express a of 6.75? Anyone? So look how we expressed it here. Right, so this is an example up here for expressing it with 3 completed intervals. Now we've got 100 completed intervals. How can we express that? What's it going to be like? What's that? Why? He said summation notation. What's that? Easier way to write what? But what would I be writing out? What's that? I'd have to write this out 100 times. Do you understand? I would have to write this out 100 times, but they're all so close, right? And we know each one of these x values is. Each one of these x values is simply what? It's the same. So given that j changes from interval to interval, we know every x value is that. So every one of these bits of accumulation for a current interval can be written how? How can I generically write the accumulation for one completed interval? How can I generically write the accumulation for one completed interval? Sophia, you want to try that?
So we are going to go off of this like summation?
No, I just want to generically write the accumulation of one completed interval, any one of them. But just I want to write the accumulation for one complete interval and just write it once. And it could represent any of them. How would I do that?
So it would be
R
R
of
a plus j minus 1 and then times dx, or yeah.
okay.
And then the closed parentheses.
Okay. Plus. Again, I want to write the accumulation from one completed interval. How do we calculate the accumulation from one interval? So far you have what? What is that? Is that amount of accumulation? What is it? Anybody? It's the rate in any interval, right? It's the rate in any interval. So how do I get the amount of accumulation from that interval? Leo? Yeah, just like all these, right? So we're just like all these, right? So it's the rate at the left side of the interval times, oh gosh, delta x, right? Delta x. MDX, and the little amount of accumulation is MDX. MDX plus MDX plus MDX plus MDX. Okay? So, but then, how many of those are we adding together? 100. So how can we express that? Yeah, so that's where sum comes in. So we're going to sum up a bunch of these. Starting at j equals 1. J equals 1 gives us, what, 0 delta x's and gives us r of a, right? First interval. There's no 0th interval, right? The first interval is going to be r of a up to 100. Is that a of 6.75?
Well, no, because you have to still include the 101st interval.
Right. And how would I do that?
It would be if you take the summation and you add it with r of a plus 101 delta x
Times dx now? How do you do? Is it right? Autumn likes it?
I don't know. Why?
Noel?
Just shift it down.
What's that?
Should the delta x and the r, well, the second r, be a dx as well?
What does this mean? What is this doing for us? A plus. So what is the meaning of that? What should it be? Should it be dx there?
So what this is doing is it's taking like the right-hand rate of our interval.
Okay.
So it means it should be 100, so it's the left-hand rate.
100 instead of 101. Everything else is right. Brandon, what do you think? You agree with that? Yeah, so we have 100 completed intervals, right? We have 100 completed intervals. So, but now back to this question. Should these be just be delta x? Sorry, this is times, not over. That's misleading. I just ran out of room. So this is times dx. So should this be dx in here or delta x? dx or delta x? Some people are saying delta, but some thought it might be dx. Well, you think it should be dx or delta x?
No, I think it should be delta x. I heard your explanation, like it's the completed interval, and we're trying to get it like to one side of the interval, and it should
Right.
be the left side.
We're trying to get to the left side of the current interval. To get to the left side of the current interval, we're going across what kinds of thing? Completed intervals, right? We're going across completed intervals to get to the left side of the current interval. So those are all delta x's, right? Those are all 100 delta x's to get to the left side of the current interval. But then we're going to take that rate that we get and only multiply it by how far we've gone into the current interval, dx. Okay, so this is a kind of a blueprint for our.
Well, how does that make sense? Because
Yeah.
the one right here has 3 completed intervals.
Uh-huh.
Right? And then that's the 4th interval.
So the current interval is the 4th interval, right? So we went across 3 intervals, complete intervals to get it. The current interval is the 101st, so we went across 100. One less. Is it? Okay. So what's left? What's left is that how many intervals are there, right? So for the current value of x, the current value of x is going to go through, it's going to be not necessarily 100 intervals. Right? There's going to be a time when there's 100 completed intervals, but then there's going to be a time when there's 102 103 and 104 completed intervals. So given a value of x, the question is, how many completed intervals? And once we answer that, then we're pretty much done. Do you see that we've just written the accumulation in one line for 100 intervals? And that's a big first step. Now we just need to write it for any number of completed intervals, meaning x is going to vary through all numbers of completed intervals. So the question is, given the current value of x, how many completed intervals are there? Given the current value of x, how many completed intervals? So given any current value of x, how many completed intervals have we made it through? It's not a question you can answer right now. But this is the next question we have to answer. Given a situation with an a value and a delta x, with delta x and an a starting a value, and then a current value of x, how many completed intervals do we have? Yeah. Hold on a second. So you just remember that. So we're going to develop. Oh, no, that's great. Maybe you don't. Maybe you don't. That's great. But no, that's awesome. No, that's totally awesome. But let's. I don't want you just to spill the beans. But no, that's great. If you're coming up with it off the top of your head, that's really good. Okay. So here's that situation. And this is so here we have the situation. I've got a is 2.1. If you look up there, a is 2.1. Delta x is 0.83. And x is varying through intervals, right? So for any value of x, there's some number of completed intervals. So if I come over here and I just pause it. So given this situation, a is 2.1, delta x is 0.83, and the current value of x is 11.59. How many completed intervals are there? Find it however you can. Any way you can. I don't care how you do it. How many completed intervals are there from a to the current value of x, given this setup? A is 2.1, delta x is 0.83, current value of x is 11.59. Do it any way you want to do it. I don't care. What do you mean you count it? You can't do it that way.
I didn't count. That's not how I did it.
No, I told you you could do it anyway. So yeah, you can just count. There's just 11, but what if? There we go.
I wanted to see if I could count them.
Well, that's not the goal here. Okay. Yeah.
Like 0 and 1.
What's that?
001.
And how, so did you? What? How did you get that? I just changed it, by the way. Did you?
Yeah, that's 65.
This one is?
Yeah. The other one was 55.
Oh, okay. So did you guys? We were talking about something else. But so now, Leo, you want to share what you came up with? Okay, and what's that mean? What does x minus a? So I'll do x minus a. So that would be, okay? From here to here. Is that right? X minus a. So that's that. It's the length of the interval from a to x, right? Final minus initial, right? Final minus initial gives us the amount of change, right? From a to x. All right, then what do you want to do? Divide by delta x. And what does that do? Okay, so yeah, so if we divide by delta x, saying we're partitioning it up into widths delta x and asking how many we have. What do you get for that? What was it? 65.44. So I'll say 65.45. Okay? So how many completed intervals? 65, right? What does the 0.45 represent? Yeah, so it's like the percent or the portion of the current interval that we've traversed, right? So this is like the percent. We're 45% of the way through the current interval, right? And we don't want that because all we want to do is count the number of completed intervals, right? That was our goal, just the number of completed intervals. So portion of current interval. All right, so this formula is what? A minus x over. And then we, oh, sorry. Thanks. And what do we want to do? We want to take that value and what do we want to do with that value? Yeah. Subtract, yeah, well, it's actually not dx, but we want to get rid of the decimal, right? You want to chop off the decimal. So there's a mathematical function that does that. Some of you know it. The floor function takes a value and just truncates off the decimal part. That's exactly what we need, right? So you write it this way. It's written this way. So it takes whatever values inside those bars with the floor bars on them, and then takes what? The greatest integer less than that. It takes the greatest integer less than the one you put in, meaning it just chops off the decimal part. That's exactly what we want. It's called the floor function. So we're going to use the floor function on this ratio of x minus a to delta x. So in GC, you just type floor and it pops up. As soon as you finish typing the word floor, it pops up. And so then inside you can do 11.59 minus 2.1 all over 0.145. And it gives you, it returns 65. It does not return 65.45 because we're putting it in the floor. It just takes off the 0.45 and returns 65. Yeah.
Does this work also on Windows, or is it like only a Mac thing?
That should work on, PC. Yeah, it should definitely work on PC. Just type the word floor. Okay, and what, so this whole thing gives us what again? So what did we find? What about, what does it give us about the completed intervals? Yeah, amounts, number of, right? So there's number of completed intervals. Okay, and so what about now? Let's make that smaller again. We've got the number of completed intervals. Another thing we're going to need is the value of left of x. So left of x, here's the thing about left of x. It's different than most functions you've seen because what the independent value is x, the current value of x, and what kind of thing is the dependent value of left of x? What kind of thing do you get as the dependent value of left of x? Right, and what kind of value is that? Is that an x or a y? Another x. This is a confusing thing for students. You really have to remember this. In left x, you put in the current value of x, and it spits out another x. It doesn't spit out a rate. It doesn't spit out a y value. It doesn't spit out amount of accumulation. It spits out another x value. The value of x at the left side of that current interval. So can you write a formula for left of x? Can you write a formula for left of x? That's what we'll work on now at your table. what is a formula that will give you the left side of the current interval?
That's such a lot. Everyone does. That's such a lot. Everyone does.
Okay, so I actually want everyone to think about that and kind of work on it and convince yourself that you've done it right. We're not gonna. So everyone work on it, okay? That's what we want to. We're ready to finish the one-line A function now that we have all the pieces we need. Okay, so how many completed intervals to reach the current interval? What did we find? How many completed intervals to reach the current interval? What's that? Sorry. Okay, here we go. So how much do we have at any current value of x? So the general scheme is that we're going to have accumulation due to the completed intervals plus, and did we find that it was this? Sum up r of the x value at the left side of every interval, completed interval, times delta x, right? Just all this is mdx plus mdx plus mdx for the completed intervals plus accumulation so far in the current interval would be r of left of x, right? It would be, this function is going to give us the left side of the current interval, so r of left of x times dx. So then the question is, what's dx? What is dx in terms of x? How could you write dx in terms of x? What amount of change is that? Okay, you got the right idea? X minus left of x. Yeah, so dx in the current interval would be x, the current value of x, minus the starting x in that interval, x minus left x. Oh, but we're not there yet, sorry. How many completed intervals are there? So what we're going to sum up from j equals 1 to the number of completed intervals. And we figured that out. That's what Noel said, right? It's the floor of x minus a over delta x. How many complete intervals there are. And then dx is the same as x minus left of x. So we did it. That does it in one line. The same thing that no matter how small delta x is and no matter how many thousands of completed intervals there are, this is going to do it. It's going to sum up all the accumulation of the completed intervals plus accumulation so far in the current interval. So this is the one-line version of that accumulation function. So what I somewhat didn't really confirm altogether, which I want everyone to think about and talk about, is what is left of x, right? So what is left of x? So we need that function as well. So what I want you to notice about this function is, can you imagine writing this function if there was no such thing as function notation? Why is function notation so crucial in this situation? Where do you see function notation in this? Everywhere, right? So r of, right? We need to call upon all these different rates. For every completed interval, we need to call upon its constant rate. So we're going to use r. So without that function notation, this is kind of like impossible. And then also, left x is going to make our life a lot simpler here by knowing that that's the x value at the left side of the current interval. Left of x. And then r of left of x. Okay, so yeah, so function notation is everywhere. And even this floor is a type of function, right? The floor is a function. So where it's not function notation per se, it's the same idea that those symbolisms perform this operation, right? So without this notation, floor function and function notation for r and left, this would be a lot messier, longer, if not impossible to write. Okay. Any questions? So again, this does the same thing as that. Remember the basketball rocket, A of x, that we have. But now it achieves it for any number of intervals. So you could go on thousands, tens of thousands of intervals. Each before we had to write with its own individual line segment. This can do it now. This can write it all, the whole piecewise function in one line. Okay, so assessment on this Thursday. And the next GC file, which will be, so let's talk about that. The next GC file is this one. For a week from Thursday.
We're gonna do that?
Yes, this is what you're doing next. Yeah, so if you have a Mac, that will be easier. I don't think you can drag and drop. So I'll show you on Thursday how you can drag and drop symbols onto points in GC, and then it'll show that symbol at that point. So anything in the, if you go to the math menu, the text, the edit. So on your Mac, there's the emojis and symbols menu, and you can pull that up. And then any of these things. Okay, I'm talking, guys.
Is it on PCs though? No. So we don't do that?
Yeah, so if you just have some kind of symbol that just is some kind of pointing symbol, that's fine. It's like even like an up caret or something like that. It's fine. So that's just, that's just fluff, right? It just looks cool. But the mathematics is the important thing, and having it work. That's the important thing, that it works. Okay, and so if I come in here and change the function, so this is the current function that I'm showing. Come in here and just show, 1/5 x squared. No, I want 1/15 or 1/25. There we go. So even all you have to do is change the function, and it's working for that function. But see, that's the beauty of functions, is that if you use them, then you can create something like this, and all you need to do is change the function, and it
Does it matter
does.
what we make our A and
Well, so in the file, A is changeable again. So here you come up here and you make A.
So in our file, it doesn't matter what we make our A or delta x or x, does it?
You have to make it so that the user can change A to be anything, like this. So now I just changed A to 0.5, and now it starts at 0.5, and the A symbol is at 0.5. And then you can change the delta x. Make the delta x 1.6. 1.6, that's what I want. 1.6. And now delta x is 1.6 for the new function with a new A value. All you have to do is change those parameters, and it works. Yeah?
Is there a symbol for delta x on PC?
So yes, again, so you're going to have to come up with an alternate way, like two letters. So you distinguish between dx and delta x. On a Mac, it's option J. Is that right? Yeah, option J on a Mac gives you delta. But again, GC doesn't know that delta x is what we are thinking of as delta x. That's just two characters. So you got to use the backslashes. If you're going to use delta x, you got to use the backslashes to make a character string to be your delta x. Just like if you were using a word for a parameter or variable. It doesn't. If you type in delta and then x, it doesn't know. It just thinks that's two different things multiplied together. Okay.